Welcome back. Functional Analysis FAV 018 by Prof.Dr.A.G.Srinivasan. This video has two parts. First part is FAP 005, the prerequisite of functional analysis. The second part will be introduced on Banach spaces. Let X be a non-empty set. So we begin with a non-empty set X. A relation or an operation, also called as a binary operation, is a subset of X cross X, where X cross X is the Cartesian product of X with itself. So a binary operation is a subset of the Cartesian product X cross X. Definition: let X be a non-empty set. We bring in plus as a binary operation defined on X. We say X plus is a group if it satisfies four conditions, which are closure, associative, identity, existence of identity, and inverse. What is closure? For every AB belongs to X, A plus B belongs to X. For every ABC belongs to X, A plus B plus C is equal to A plus B plus C. For every A belongs to X, there is a 0 belongs to X such that A plus 0 is equal to 0 plus A is equal to A. And this property is called existence of identity. And 0 is called identity element. The fourth property is that for every A belongs to X, there is an element called minus A belongs to X called inverse element, such that A plus minus A is equal to minus A plus A is equal to 0. And this is called existence of identity. Inverse. If X comma plus is a group, then 0 is called additive identity and minus A is called additive inverse. Well, the plus is only a symbol or a binary operation of X. Note number 2, if X comma plus is a group, it should be a group first. If for every AB belongs to X, A plus B is equal to B plus A plus B is equal to B plus A, then the group is called an abelian group or a commutative group. For every AB belongs to X, A plus B is equal to B plus A. Any X satisfying 1 is called groupoid. That is, if it satisfies only the closure property, it is called a groupoid. If it satisfies the closure property as well as the associative property, it's called a semigroup. If it satisfies the closure property, associative property, and identity property, it's called a monoid. So, if 1 satisfies, it's called groupoid. 1 and 2, it's called semigroup. 1, 2, and 3 are called monoid. Note that every abelian group is a group. Every group is a monoid. Every monoid is a semigroup. And every semigroup is a groupoid as well. Certainly, the converse need not be true. What is a ring? A ring is a non-empty set associated with two operations, plus and dot. We call addition and product. X comma plus is an abelian group. X comma dot is a semigroup. And for every ABC belongs to X, A plus B dot C is equal to A dot C plus B dot C. A dot B plus C is equal to A dot B plus A dot C, which is called distributive properties. So any X with these two operations, plus and dot, satisfying 1, 2, and 3 is called a ring. We don't study much about the ring, but the ring is used to define what a field is. So, fifth definition, let F be a non-empty set with two operations plus and dot. We say F comma plus comma dot is a field. We say this is a field. If F plus is an abelian group, F minus 0, that is, other than the additive identity, all the elements under the dot is again an abelian group. And for every ABC belongs to F, A plus B dot C is equal to A dot C plus B dot C. A dot B plus C is equal to A dot B plus A dot C. The distributive laws satisfies. So a field is the one satisfying this, this and this. A vector space, or we call a linear space, over a field K. The group, the ring, the field are independent entities, whereas a vector space depends on the field. So a vector space or a linear space over a field K is a non-empty set X of elements x, y, etc. called vectors, together with two operations called vector addition and scalar multiplication. So there are two operations. One is called vector addition and scalar multiplication. The elements of the field K are called scalars. There is an operation called scalar multiplication. We will see what it is. Under vector addition, for every xy belongs to x, x plus y is equal to y plus x. For every xy z belongs to x, x plus y plus z equal to x plus y plus z. There x is a 0 belongs to x, called the 0 vector. Now because x is going to be a vector space, I call this 0 as a vector, such that x plus 0 is equal to 0 plus x is equal to x for every x belongs to x. For each vector x belongs to x, there is a vector called minus x belongs to x, such that x plus minus x is equal to minus x plus x is equal to 0. The 0 is additive vector addition. Not only that, the fifth axiom is that for each vector x belongs to x and a scalar alpha belongs to k, the product called scalar product is defined as alpha x, such that for every xy belongs to x, alpha beta belongs to k, we have alpha times beta x is equal to alpha beta into x. 1 belongs to k, an identity with respect to the product of the field with 1x is equal to x. And the sixth axiom is that alpha times x plus y is equal to alpha x plus alpha y. Alpha plus beta x is equal to alpha x plus beta x. So any vector space will satisfy the six axioms. 1, you required a non-empty set. 2, you required a field. And you require two operations called vector addition and scalar multiplication, satisfying 1, 2, 3, 4, 5 and 6 axioms. Note that if 0 belongs to k, it's a scalar, where theta is a symbol used for identity in x. Of course, we wrote it here 0, but we are also writing as theta, just to differentiate the zeros. So 0x is equal to 0, actually theta. Alpha theta, that is alpha 0 is equal to 0. This is a vector, this is a vector, this is a vector, and this is a scalar. And minus 1 is additive identity in the vector addition. Minus 1 into x is denoted by a symbol minus x. K is called a scalar field or a coefficient field. If the field is equal to the real numbers R, set of all real numbers R, we say x is called a real vector space. When I say a real vector space, it is not real. The field is a real. Okay, x can be any abstract space, but the field used for the vector space is real. In the same way, we define a complex vector space if k is equal to c. Now, this is the first part of the FAP 005. Let's continue with the second part of the video on the functional analysis part. So let's go to the definition. What is x? Let x be a real or a complex vector space. So it's a vector space over a real field or over a complex field. A norm denoted by this symbol, which we will be pronouncing as norm, is a real function x such that at each x belongs to x, there is a number associated to the norm. So for each x in x, there is a real number norm x, denoted by norm x. See, for example, if you take a class, in a class, each student is given by a number, let's say roll number. So in the class, a person, David, is called roll number 1. Stephen is roll number 2, and so on. So though roll numbers are numbers, but they are not same outside the class. But inside the class, whether it is David, it is 1. Whether it is Stephen, it is 2. They are same. So this is an association of number to each element of the class. In the same way, you have a vector space x. For each x, we associate a number called norm x. Norm x is a real number. It's a real number. Please remember, it is a real number. Satisfying the following property. For every x, norm x must be greater or equal to 0. Norm x is equal to 0 if and only if x is equal to 0. Norm of alpha x is equal to modulus alpha into norm x, where alpha is in R or C, because the vector space we are taking is a real or a complex vector space. So alpha must be a real or complex. So the modulus will be defined based on that. And the triangle inequality of the norm is norm x plus y is less than or equal to norm x plus norm y for every xy belongs to x. And this is called the triangle inequality. So norm will satisfy these four axioms. Norm x greater or equal to 0. Norm x is equal to 0 if and only if x is equal to 0. Norm of alpha x is equal to modulus alpha into norm x. Norm x plus y is less than or equal to norm x plus norm y for every xy belongs to x and alpha belongs to R or C. Let's go next definition. This is a definition. A normed space, also called as normed vector space, also called as normed linear space, we'll be using NLS hereafter, is a vector space with a norm defined on that. So a normed linear space or NLS is a vector space. It's a vector space defined over a field with a norm on it. So norm means the field must be real or complex. That is, a norm linear space with a norm, this is a norm we talk about, is denoted by x comma norm or simply x. X comma norm or simply x. Henceforth, we only use a norm linear space. Let x comma norm is equal to x be a norm linear space. Denote a metric D. I of course use the word metric now, but we will see it's a metric in fact by the formula d of xy is equal to norm x minus y. And you can easily check that this D gives you a metric, and this metric is called the metric induced by the norm. Okay, so begin with a normed metric space. We begin with a norm linear space. We define a metric, and we get a normed linear metric space. We get a normed metric space or metric space which is a normed linear space. So x is a normed linear space. It should be a vector space first, and for each x and x there is a real number associated satisfying these axioms, which are called star. We call it a star, and we also have a metric defined on that. A norm linear space is a metric space. We already proved it, because for the given norm you can define a metric, and showing its a metric is very, very easy. A Banach space is a complete norm linear space. What is a complete norm linear space? Every sequence, every Cauchy sequence converge. So refer the previous video on complete metric space. You will understand what is a complete metric space. So a norm linear space which should be complete, if it is complete, it's called a Banach space. Before we investigate much about Banach spaces, we make some interesting observations. Suppose you take R or C, which are real numbers or complex numbers, is itself is a metric space, is itself is a normed linear space with the metric, with the norm x is equal to modulus x. And every norm linear space, every Banach space are certainly metric spaces, but not the converse. A metric space need not be a Banach space. A metric space even need not be a norm linear space. Finally, we are going to have one more important result, which I'll be using it in the fourth result of today's video. If x comma norm is a norm linear space, for every x comma y belongs to x, modulus of norm y minus norm x is less than or equal to norm of y minus x. We are going to show this result to define the continuity of the metric space. Now proof is very easy. It's only 2 minutes it takes. We know that modulus a less than or equal to b if and only if minus b less than or equal to a less than or equal to plus b. You know that. Now to prove this, it's like modulus a less than or equal to modulus b. It's like that structure. So we will show that minus norm y minus x is less than or equal to norm y minus norm x less than or equal to norm of y minus x. So we are going to show this star. Now first we call y minus x is equal to t. I just call y minus x is equal to t. So simple mathematics tells you y is equal to x plus t. So norm y is equal to norm of x plus t. Take norm on both sides. Norm y is equal to norm x plus t. So you can check that here. But norm x plus t is less than or equal to norm x plus norm t by triangle ending of the norm, right? Now, I'll bring this x this side. I'll bring this x this side. Okay, this x I'll bring this side. So what we have is norm y minus x is less than or equal to norm t. But what is t? T is y minus x. I'll put norm y minus x is less than or norm y minus norm x less than or equal to norm y minus x, which I call 2. Now interchange y and x. What do you get? Norm x minus norm y is less than or equal to norm x minus y. I've interchanged y as x as y, so I get this automatically. But then the norm x minus y, if we investigate, the norm x minus y is norm of minus 1 of y minus x. There's an x here. So that you will see that minus 1 can be taken with the modulus, and modulus of minus 1 is plus 1. You get norm y minus x. So norm x minus y is norm y minus x. So what I have is norm x minus norm y is less than or equal to norm y minus x as well. Now, when you put the negative sign on both sides, the inequality will be reversed. So norm of minus y minus x minus norm y minus x is less than or equal to minus of this, which is norm y minus norm x when it is LCM. So minus of norm y minus x is less than or equal to norm y minus norm x less than or equal to norm y minus x from equation 1. We already proved it in equation 2 we proved it. So what we have is this is less than or equal to this, less than or equal to this, which is the star. So you can see what the star is. The star is that. So we proved that modulus of norm y minus norm x is less than or equal to norm y minus x. We are going to use this to prove the following theorem. A very interesting theorem. If x comma norm is a norm-linear space and define t from x to r defined by tx. So in functional analysis, we don't write t of x, we only write tx. Okay. So tx is equal to norm x. So this is my t definition. T is from x to r. We define tx is equal to norm x. We are going to show in one stroke that t is continuous. To show t is continuous, recall in the previous videos, t is continuous. Given epsilon positive, there is a delta positive such that whenever norm x minus x naught less than delta, then modulus, of course this is modulus, maybe in continuity function, modulus tx minus tx naught less than epsilon. Now here x and x naught is chosen from the first x, therefore there is a norm in that, and tx and tx naught is in r, therefore there is a modulus symbol, because we already saw in real norm x is somewhere I wrote it here, norm x is in r, norm x is mod x. So we can use that. So this is what we are going to show in this class. Now we'll start with modulus tx minus tx naught. But what is tx definition? Tx definition is norm of x. Tx naught is therefore norm x naught. So tx minus tx naught is actually equal to modulus of norm x minus norm x naught, is actually equality. But this is less than or equal to x minus x naught by the just now theorem we proved. But this is less than delta we assumed, because that continuity that this is going to happen always for the delta. So for that delta you can choose epsilon as delta. So you find tx minus tx is delta and delta, therefore t is continuous. Delta can be anything existing, and you can take epsilon as delta itself. So therefore if t is a mapping from tx x norm x, it is easy to show that t is continuous. And finally we are going to have a comment. Every Banach space is certainly a non-linear space, but not the converse. We will show a little later in subsequent videos that a Banach space need not be a non-linear space need not be a Banach space. See you soon in FAV 019. This is Dr. A.G. Srinivasan. Thank you.